A new drug, A, cures about 72% of patients. The old drug, B, cures 75%. So B is the better drug, right? But split those same patients into mild and severe cases, and something bizarre happens. Among mild cases, drug A wins. Among severe cases, drug A wins too. Drug A wins in every subgroup, yet loses overall. The exact same data tells two opposite stories. This is Simpson's paradox, and once you see it, you can't unsee it. Let's put real numbers on it. 200 patients take each drug, split between mild cases and severe ones. Mild cases are easy to cure. Severe cases are hard. Hold on to that. It turns out to be the whole secret. Before we count, sit with the puzzle. A drug that wins among the mild and wins among the severe. Could it really lose overall? Take a guess. It feels impossible, the whole disagreeing with all of its parts. Let's see exactly how. Start with the mild cases. Drug A cures 63 out of 70. That's 90%. Drug B cures 120 out of 150. That's 80%. Drug A wins. Now the severe cases. Drug A cures 80 out of 130, about 62%. Drug B cures 30 out of 50, 60%. Drug A wins again. So in both groups, A is the better drug. 90 beats 80, 62 beats 60. The conclusion looks airtight. But now just add up the totals. Drug A, 143 cured out of 200. That's about 72%. Drug B, 150 out of 200. 75%. Drug B wins overall. The trend has completely flipped. Let that sink in. The exact same patients, the exact same recoveries, and yet the answer to which drug is better flips, depending only on whether you split them or not. How can a win every battle but lose the war? Look at who actually got each drug. Drug A was mostly given to severe cases, the hard ones, where cure rates are low for everyone. Drug B mostly went to mild cases, the easy ones. So drug B's higher overall score isn't because it's better. It's because it was handed easier patients. A hidden variable, the severity of the case, is pulling the strings. When the groups you average over are lopsided, and tied to the outcome, the overall number can point the opposite way from every single subgroup. And let's be clear about what that means. Drug A really is the better choice for a mild case and the better choice for a severe case. There is no individual patient for whom drug B is the wiser pick. There's a beautiful way to picture this. Think of each group's result as an arrow. The steeper the arrow climbs, the higher the cure rate. Drug A's two arrows are both steeper than drug B's in the mild group and in the severe group. A genuinely wins each. But to combine groups, you don't simply average the steepness. You add the arrows, tip to tail, weighted by how many patients sit in each group. And because drug A's patients pile into the shallow, severe group, its combined arrow gets dragged down, below drug B's. The total can lean the opposite way from every single part. It's a vivid picture of the whole effect. A clean trend in every single group can vanish, or flip entirely, the very moment the groups are pooled together. And this is not just a textbook trick. In 1986, a real study compared two treatments for kidney stones, traditional open surgery and a gentler keyhole technique. For small stones, open surgery succeeded 93% of the time, against 87% for keyhole. For large stones, 73% against 69%. Open surgery won in both. Yet overall, keyhole came out ahead, 83% against 78%. Why? Surgeons sent the hard cases, the large stones, mostly to open surgery. The very same trap with real patients. And notice the bind it puts you in. Pool the data, and the keyhole method looks best. Break it apart, and open surgery wins for whatever stone you actually have. The same figures give opposite advice. It strikes in famous places too. In 1973, the University of California, Berkeley, appeared to be admitting men at a much higher rate than women. It looked like clear bias. But department by department, women were admitted at about the same rate as men, or higher. The catch: Women applied more often to the most competitive departments, where almost everyone was rejected. The aggregate told only part of the story. Wherever a hidden variable shapes who ends up in which group, Simpson's paradox can strike, in medicine, economics, sports, and policy alike. Sport has a famous case. Across the 1995 and 1996 baseball seasons, the player David Justice had a higher batting average than Derek Jeter in each of the 2 years. Yet over the 2 seasons combined, Jeter's average came out clearly higher. Justice beat him each single year and lost across the pair. The reason is that same hidden weighting. Jeter came to bat far more often in 1996, his stronger season, so that year counted much more heavily in his combined total. 2 seasons, 2 clear wins for Justice, and the combined crown for Jeter. Simpson's paradox, printed on the back of a baseball card. Medicine, admissions, baseball, the same shape again and again. A winner in every slice can still be the loser once you add them up. So should you always trust the subgroups over the total? Not blindly. It depends on what that hidden variable really is. If it's a common cause, like stone size, which shapes both the treatment chosen and the chance of success, then the subgroups tell the truth and the total misleads. But if the variable sits on the path from cause to effect, a stepping stone the treatment works through, then splitting by it actually hides the real effect, and the total is the honest one. The numbers alone can't tell you which. You need a picture of what causes what. That, in the end, is the real lesson of the paradox. And this pattern is older than you might guess. It has tripped up scientists, doctors, and even courts of law again and again. The effect carries the name of Edward Simpson, who wrote about it in 1951, though the statistician Carl Pearson had brushed against it in 1899, and George Yule laid it out in 1903. So how do you guard against it? When you meet an aggregate, a single headline number, ask whether it quietly blends groups of very different sizes. And ask the harder question, is there a lurking variable shaping who lands in which group? If there is, that one tidy number deserves your suspicion. The deeper lesson is humbling. A single number, a percentage, a national average, can hide a story that reverses the very moment you look closer. Data doesn't speak for itself. The way you slice it shapes the conclusion. Always ask what's been averaged together and what causal story lies underneath. Simpson's paradox is a warning written in plain arithmetic. The whole can disagree with every one of its parts. So the next time a statistic feels obvious, pause and ask what's hidden in the mix.